Eli Glenn, and this is Kevin Losterville. Thank you. And we are the two engineers in charge of this project from Blades Incorporated, which is made from our names. It's just us two. Small company. And we are here to present to you our 64-bit processor, the 440X. It's awesome. So let's skip over that. We just introduced ourselves. And
so first, for the baseline, we're going to go over the instructions for the baseline, the memory structure, the registers, the addressing modes, the flags, the data types, and how we handle the interrupt and reset.
All right. So to start, we start with 80 baseline instructions. This includes triple, double, and single operand instructions. Hopefully all of you are familiar with what that is. And I am having difficulty not functions. There we go. And then conditional jumps with all the unconditional jumps, immediate operands, flags, and floating point operations. Kevin?
So the memory structure is a little endian format with the least significant bit being on the right. And our memory, since our memory is 32 bits, it's stored in two trailing words with the most significant bits on the higher memory area.
All right. So now we also have some just basic sets of registers in our processor. We have two sets of 32 general purpose registers. One set for the integer data path, another set for the floating point data path. All of them are 64 bits wide in our BIU, the bus interface unit. All registers are 32 bits. Such as the instruction pointer, instruction register, stack pointer, memory address register, all of our buffers. And the only exception to that 32-bit rule in the BIU is a 64-bit temporary register that we had to implement for our exchange operation, exchange or swap, however you want to word it.
The flags are taken from the integer data path and the floating point data path. And from the integer data path, it gets the N, Z, O, and C, or -0 overflowing carry. And the interrupt enable flag comes from the CU. And the floating point data path flags are greater than or equal, less than or equal, equal and not equal. And then we combine them in the BIU into a flags register. And we'll go into more detail on that later. And the data types, we only have 64-bit integer and 64-bit floating point. And the integer has an unsigned range of 0 to a large number, and the signed range of other large numbers. And for the floating point, it has one signed bit in the most significant field in the higher memory area, and followed by an 11-bit exponent field, and then 52-bit fractions, but the 32 right down there is for extra accuracy.
Now, for our addressing modes, we did have immediate register and indirect addressing modes. For the immediate, we had to use 8-bit, 32-bit, and 64-bit operands in those modes. A register, it's just a definition of operand that is contained in the register. Register indirect, exact same thing. Operand is a value contained at the memory location pointed out by the register. And so the resets and interrupts, we implemented them. We hope it's unique. Basically, the reset, the processor will not start unless a reset is implemented beforehand in the program. When the reset is implemented, though, it basically sets the IP and the stack pointer to their default values. Interrupts, they are generated in a peripheral I/O module just for simulation purposes. We implemented it at the interrupt enable. This part right here, though, would normally be an interrupt request, but that, again, this is just for simulation purposes. And now onto the processor design, more fun stuff, and extending off the baseline.
So the top module consists of the CPU and the data memory and input and output modules. And the only thing going into the CPU is the interrupt, the reset, and the clock, and that comes from the test bench. And it instantiates the memories, all the data comes from the EU module, and all the control signals come from the CU module. And it's also from the EU module to the I/O module is the interrupt acknowledge and interrupt enable flag.
The only outputs from the CPU is, in fact, just the data addresses and the memory memory control signals. Now, again, as Kevin mentioned, the CPU does combine the CPU and the EU. The control unit, almost all of its outputs go straight to the execution unit. That tells control unit is the finite state machine that controls what is executed when. However, it does take two inputs in forms of our 11-bit flags register and our 32-bit instruction register, and again, it shows it outputting the memory control signals and the memory addresses there. Inside our execution unit, though, it's fairly basic. This is very similar to the baseline. There were very few changes hardware-wise. We implemented two data paths and a bus interface unit. Are there any questions on how those interface with each other? Everyone understands the baseline? Okay, I'm seeing nods, yeses. I'll take that as a yes.
So the BIU is the module that we had to do the most changes on to get all the instructions to work. And we're going into more detail on it with the code after we go over it for the next one.
Okay.
For our close-up, this is where we implemented the flags register, where the C and Z and O flags are coming from the ALU out from the integer data path. The interrupt enable comes from the CU for when the interrupt is called, when it wants to set it. And the floating point status comes from the floating point ALU, integer data path, and then we combine it all into one register and then send that to the control unit for the conditional jumps. And the floating point buffers, we didn't change anything from the baseline. But the read buffers, we added two sets of muxes. The first one is to decide whether the data comes from the instruction memory or the data memory. And the second one is to determine if it gets 32 bits of 0 or that data. And if we get 32 bits of data for instructions such as OR high, which would get read buff 0 would get 32 bits of 0, or the floating point load or load immediate.
Okay.
And then there's the temp register that we added. That comes from the R value in the integer data path. And it goes in the temp, and then that can decide between read buff, what it gets, either these read buffers or the temp value.
Next slide?
Yep.
Okay, let's check.
And then the MAR and the stack pointer, we added several inputs for it, which we'll go into more detail later. And the mux down here decides where the G address comes from, the MAR and the stack pointer. Then the write buffs are similar to the read buffers in that they can get 32 bits of 0 or the data from the ALU. And then the instruction pointer also has several inputs for jumps and stuff like that. And the IR only comes from the instruction memory.
Okay. Alright, so now just talking about the buffer registers, the write buffer registers. We have two sets. We have one for floating point buffer. This is, of course, the output from the floating point data path, and our write buffer just is the output from our integer data path. The floating point has not changed, but again, as Cody mentioned, the write buffers can receive 32-bit 0 depending on what the instruction is, and he also explained how
it will only do it if write buff load is enabled.
Right, it will only load write buffer. Right.
So the read buffers are, like I said, similar to the write buffers, and they will also only load if the load is enabled. And the IR register, again, will similar, only does it if load is enabled. So we added several.
Sorry, I bumped a button.
To make it easier to control the muxes, we concatenated the control signals up here into one, so it's easier to just look at and understand what's going on.
Okay. Now, for the MAR, the memory address register, we implemented a case statement. So the MAR will either stay the same, take input from either the integer data path or the floating point data path, increment, or if it's an interrupt, it will automatically set to 3FFX.
Because that's where we have the ISR.
Yes.
And then the stack pointer on reset, it also gets 3FF for the ISR. And they can decide between keep staying the same, decrementing, incrementing, or getting IR extended for the load immediate instructions.
Alright, so our instruction pointer has quite a few functions. Again, though, it's very similar to the memory address register. It can either stay the same, increment, it can receive output from the register or from our IR register for IP load instruction. It can also take input from read buff 0 and of course the concatenation of signals for jumps.
And the flags, we put a load enable on it so that not all instructions change the flags, like load should not change the flag. But we have the flags load control signal in every state, so we just make sure nothing happens that we don't want it to. And the temporary register will only load with the load enabled. And here we have all the data assignments and final assignments of muxes and stuff. So the data up here can decide between the write buffers or the floating point buffers, and if none of those are enabled, the output enables are not enabled, it will get high impedance. And for the read buff, it can choose between the temp register and the read buff registers, and it will only, and to choose between it, you need to pick up the temp output enabled. The IR extended is just a sign extension that everyone else has. And the D address decides between stack pointer and MAR for the D address mux. And the IO address will always come from the MAR. And then these final two read buff mux decide where the data comes from for the read buffs. It's the first set of read muxes for the read buffers.
So that was the BIU. It is very important to us. So this is our floating point data path. It has not changed from the baseline, but we felt we should include it in this report, just in case anybody has any questions. Now, our integer data path has one important difference from the baseline, and that is this amazing barrel shifter. It's the only thing I'm really going to tell you about it right now, so we're going to get into more detail later, is that it passes S as its default, and it'll perform all the amazing operations later. We also did have to expand S-select, though, to account for the 8-bit immediate instructions, such as subtract immediate, add immediate, etc. And this is our S-select. As I mentioned, it will receive either S, which is that out from the barrel shifter, the DS, or the 8-bit immediate, and its default stays the same. And now we're getting into, well, our really awesome stuff, the enhancements. This is why we're all here, folks. We have two types. We have the enhanced instructions and the barrel shifter. Our enhanced instructions are almost a baker's dozen, but 2 less. So that's 11. I'm sorry. But that is the types of enhancements that we have. These are a little bit more in-depth. We can refer back to it. If any of you have any questions, please raise your hands and ask as you get them.
So the first types of instructions we added were rotate left with carry and rotate right with carry. In order to implement these, we had to make an addition to the ALU. And for the rotate left with carry, it was just a simple making the rotate through the carry. And this, for left, this most significant bit of the data will go into the carry, and the carry bit would go into the least significant bit of the data. And the exact opposite with the rotate right with carry. And it uses...
Sorry, I thought you were done.
And it only needs the source register and destination register in the opcode. And another type of instruction we added were decrement jump if not 0, decrement jump if 0, increment jump if not 0, and increment jump if 0. In order to implement this, it required a new instruction format. So we kept the opcode the same, but the source and destination register had to be the same because we're decrementing and updating the exact same register. And we also had a displacement for the jump value, and it has 16-bit range so in order to fit it in one line. And to check the 0, and all the instructions check the 0 flag, and in order to do that, we added an IP jump control signal, and that checks the flags register in bit 1, which is where we have the 0 flag. And if it's a not jump if 0 flag, then that would be 0, so we have to do a not sign in front of it, so it becomes a 1.
All set? Yep. Alright, so we added a couple of instructions that are similar, but fundamentally different in how they're implemented. The first one is our squared instruction. It basically will read the the byte for the R register and put that into the R address and the S address, so a register will be multiplied by itself and output a 128-bit product. The next one, though, is Kevin's slide, so it's not the one I was thinking of, but it's still pretty cool.
So we also added a load immediate 64-bit, because the one we have is only 32-bit, so you have to do an OR high to make it 64-bit, so we just eliminated a process. And it's exactly the same, almost, except it has, in the first state, we take away rebuff 1 getting 32 bits of 0, because that's the next state, and that's next state. And then this last state is the same as rebuff, as load immediate 32-bit, except because it the register gets both rebuffs.
Okay. Now, this is the instruction I was talking about. It is my pride and joy. It is a power operation, so basically the destination register will receive the R register to the RS register, so that's pretty cool. But the way we made it was interesting because we took the algorithm that we were given by our client for the 128-bit product for multiplication, and we implemented it in such a way that after the pre-process, it will instead repeat S minus 1 times to therefore get you correct product of R to the S. So so if the R register is 2, S is 3, it will output 8, and then 0 is the most significant word. Next, and then our XNOR and NOR operations are just simple logic operations that were not included in the baseline, but they are very handy for programmers to use. So I hope that this can be of use to our client. And this is a little test script that we did with our results being in R15, the upper part zeros, and the lower part F.
So it's formatted so if the decrement jumper.zeros, those types of instructions, if they do not work, it will halt early, and R15 will not get that value, but since it does, it works. And also the load immediate with R1 should get F0, F0, etc., and it does. And then the rest we're just testing the rotate left to carry and the square. R6 would get 4, and then square that, it should be 16 or 10 hex in R7, and it is.
Do
So
you
the
check,
biggest-
check for overflow or on a square or a power operation?
I believe it does.
Yeah, we put it in the
You
Yes.
believe it does?
Yeah,
it
we put
does.
Yeah, we didn't put it in the power code. We put it at the bottom of the ALU where it
Okay.
checks with the other
Okay.
instructions. And the biggest enhancement we made was the addition of a barrel shifter. And what it does is modifies the second operand or the S value, and it does not without affecting the value in the register. So you can have one value in the register, but say you want to multiply it by another value before performing an operation on it, then you can just do that in the barrel shifter. And it can rotate right, rotate left, shift right, or shift left. And S8 is the shift amount, or rotate amount, however much you want to do it. And it goes from the S into the barrel shifter, and then the S mux determines where the value comes from the barrel shifter or the DS, and then that goes into the ALU. But right now it's currently only limited to the triple operand instructions. So like add and subtract and multiply, stuff like that.
Okay.
And so we have control signals to determine what instructions it's performing. If none of those are selected, it will just pass S through, which is what most of the instructions do. And the shift amount is, since we have 64-bit data, it can shift up to 63 times, or rotate up to 63 times. And we could have gone through and just made a case statement and have 64 different cases and for each shift amount possibility. But to make it more faster and efficient, we split it up into 3 parts. The first one deals with the first 2 bits of the shift amount, and it can rotate the value by 0, 1, 2, or 3 times. And the second one can shift it by 0, 4, 8, or 12 times. The third one by 0, 16, 32, or 48 times. So if for example, you wanted to rotate it 20 times, then that would be 0, 1, 0, 1, 0, 0. So the first one would rotate it 0 times, because it's checking has 0, 0 as the shift amount. And then the second one would be 0, 1, or 4 times. And then this third one would also be 0, 1, or 16 times. 16 plus 4 is 20 times. So it would rotate it 20 times.
Okay.
And then the rotate left is exactly the same thing, except rotating left.
I have one thing to add to that. The carry bit is not used in the rotates currently. That is a future enhancement, possibly.
And then the shift right and shift left were just simple shifting right for the shift amount, but it checks for the control signal as well.
All right, now the format of the instructions for the barrel shifter, we had to change it a little bit, and we did something very similar to Sam Michael's project, I believe, all right, so this first bit is basically a barrel shifter enable. If that is 0, nothing is going to happen. The next 2 bits are opcode of sorts. So you have 0, 0, 0, 1, 1, 0, 1, 1, and that corresponds to these instructions. Then you have the upper 3 bits of the shift amount, and then the lower 3 bits of the shift amount over there. And we were able to fit that into our triple operand instructions. So that is what that does. And then for testing, the content values are what should be in each register. And they are. So,
future enhancements we could have added if we had more time. We started working on compare and jump if not equal and compare and jump if equal, but we didn't have enough time to implement it because it requires two source registers to compare, and then it needs a jump displacement value. But because it uses both source registers, it would have a very limited range for the jump. For the displacement value, so it would be better to add it into a trailing word, but that would require more control signals and stuff that we didn't have time for.
And then the next 2 possible enhancements were negative powers and natural log. The negative powers would basically be raising something to a fraction of itself, so that would require implementing that in a floating point operation and then reworking the algorithm for power completely, or at least for negative power. And then after we were able to dynamically adjust the base of a number, then we could pretty easily add a natural logarithmic function after that. That would all be in the floating point though. One more thing we would like to add is a conversion factor from the floating point data path to the integer data path. That currently does not exist.
And then as you saw in the VIU, it was very crowded and there were a lot of control signals. So as we went along, we just added them for the instructions to work. So it came up with like several muxes and control signals. So one of our optimizations one of the enhancements could be to optimize this data path by combining all these muxes into 2 just for each one, so so it's less money and stuff like that.
I thought you did. Didn't you just have a case statement?
We have it for some, but for others it is not completely optimized.
But for the read buffer, the code you showed us was a case statement. So in essence, it's doing, a mux that's got multiple inputs. It's just on the diagram, you kind of had to break it up, I guess.
I guess.
Yeah, to make it easier.
But actually, any case statement is like one mux with multiple inputs.
All right, and then that is our...
And then we could also enhance the barrel shifter to be able to use in more than triple operand instructions.
The CJ&E, you said you don't have much range, but don't you, let's see, you're what do you got? 18 bits are used for the 2 registers in an opcode. Doesn't that leave you 14 bits?
Well, thought they would have to add new control signals.
We would like a larger range.
14 bits. That's not
We're
good
trying to
enough.
implement it and we ran into some
Oh,
problems.
sure it is.
Ouch.
What's the ARMS range on their conditional jumps?
32K?
Huh?
Is it 32 mega?
No, just on a conditional jump?
It was 32K or 32 mega or something.
Oh, it's not
It's
32
large.
meg.
I
Maybe
think it's
32K.
Yeah, 32K.
So that'd be 16K with 14 bits.
We still would like larger.
We also ran out of time.
Yeah.
So that's the biggest problem there.
I'll tell them And that is our last enhancement. Do any of you have any questions? Yes.
Okay, so C++ has like the math.h, and a lot of compilers have libraries for this. And I'm kind of asking whether or not you've researched this is what we do, but I know it has power functions, exponent functions. I know they're just libraries where they do an algorithm for that. I know it's your power function too, but it's only 128 bits, and you're multiplying the 64-bit value to the 64-bit times. You're taking a 64-bit value, multiplying by itself 64 times.
Yeah.
So that's not going to, most of your values aren't going to fit within 128 bits.
Most of them know that is an issue that is to be addressed in our future enhancements. We didn't have enough time to work an algorithm that was large enough.
And to elaborate upon that, is doing mathematical operations like the natural log, etc., in hardware more efficient and feasible compared to whether or not just having the compiler, if it's doing a power function, the compiler would obviously write a big integer to multiple registers in order to produce that value rather than hardware. Do you think there's a trade-off between the two, or what do you see as the most important?
From the research that I was doing, as far as I can tell, hardware is, if done correctly, can be faster, which would be important. They're both just as accurate, though.
Is there an expense in hardware, though? Like doing a
The
natural
size.
log, how would you do that?
I saw that.
Would it be a lookup table of something, or?
It's similar.
Okay.
Yes.
So it takes some space on the chip.
A lot of
for
space.
Lookup table, okay.
Yeah.
I'd
Yes,
also look
sorry.
at the rotate with carry instructions again.
Sure. I'll go back to that. Rotate with carry. Oh, back.
Yeah, before the barrel shifter.
No. Before the
Oh, before the barrel.
Yeah.
Just curious how you guys.
Yeah.
So yeah, because so like rotate right with carry. How exactly is that working? Because
It's putting it's the most significant bit of the value will get the carry bit, and the least significant bits will be 63 to 1, and the carry will get the least significant bit
okay.
of the value.
What's the O thing?
Overflow?
Oh yeah, that's over.
So then,
Oh.
so what exactly is overflow doing then in that case?
I copied that one from the just rotate without carries. So I was working for that.
Rotate you'd usually consider just as a logic operation,
Yeah.
so it wouldn't affect overflow.
Okay.
Ordinarily, that's just, rotates are logic, but arithmetic shifts are the ones that affect the overflow.
Okay. Michael, you had a question?
No, it took me a while to realize. I was just going through the code.
Okay.
And it hit me.
Okay. Well, that's cool.
But actually, I do have a question regarding your barrel shifter.
Going back to
I was wondering, was it? Did you guys consider using? Because it looks like you guys are using unsigned values for your shift amount.
yes.
Did you guys consider using signed values and made a design choice to use unsigned with another bit to choose like left or right?
No, I just use signed or unsigned bit, so it can be 0 through 63. We
Okay.
can put in negatives. That was also in order to fit it into the instruction format. So we had it because we only had 6 bits available, so that's 64 for 63. So we couldn't really add negatives.
Yeah.
Now you mentioned you wanted to avoid a case with 64 states. However, I counted, I think, 16, 3 sets of 4, I believe, so 12.
Yes.
But you basically copied this, if barrel rotate right equals 1 bit 1. You have this thing, you just went over that for, if barrel rotate left equals 1. So you had taken these 12 things and copied it 4 times. Do you think that would be and did you synthesize it and look at the hardware that it produced compared to whether or not just using a case statement? Which one produces more hardware?
We did not.
check for that.
We,
Okay.
we ran out of time.
Okay, I understand.
But it's a good idea, it's, it's
Yeah.
always a good
Yeah.
idea to see if this really helped. Yeah,
Okay.
but that's if you've got time. That's a great point.
Yes. Are there any other questions? Preferably easy ones.
Well, it's not a question, but the comment, the barrel shifter's there in the data path.
Yes.
But it's only used for certain instructions, right? Like barrel shift.
Yeah, the triple alternate.
Therefore, your path is now longer because if I just wanted to use what comes out of the register file, it's got to go through all that logic.
No, it.
No.
Does it bypass? Is there a bypass?
Yeah.
Yes.
Go to the next two.
I couldn't remember if
Yeah,
I
right
saw
there.
that.
Data out is
Okay.
data in if none
Okay.
of those are
Got it.
set.
Got it. Perfect. That's good.
Okay.
Yeah.
Anybody else? No? Going once, going twice.
You guys did a great job. Both of you did a great job.
Okay.
Yeah.